So hello, everyone. It is really my great pleasure and honor to have this chance to share with you some of my recent research findings on dynamical aspects of learning linear neural networks at this wonderful event. And my name is Zhenyu Liao, and I'm now a postdoc at University of California, Berkeley. And this is joint work with Chitour and Couillet from University of Paris-Saclay. So here we go. We'll be starting with some general introduction of machine learning, okay? So the objective of machine learning is given some pair X and Y, so that can be some data, and Y they associate labels or target associated to those data, okay? And the objective is to find some function parameterized by some W so that this function maps the data X to its associated target Y. For example, in the sense that this difference is small, okay? So the first solution is a very simple linear model. So this F is just a linear function of the input X. So some matrix W times X. And this gives us the explicit linear regression solution given by this WIR if it is invertible, okay? However, the problem is that this linear regression solution is not, in general, not good enough in the sense that it may not work well for difficult problems such as image classifications and face recognitions, etc. Because it only describes a linear transformation and relation between the input and the target. So there are more complicated models. We'll be starting with the linear neural network model, which are basically inspired by the layer structure in our brain, so the connection between different neurons. So we have some data, input data X, and it's going to multiply by some weight matrices that describe, in fact, the connection between the neurons in our brain. So we get W1 times X, and that's in fact, the neurons of the first layer, and then we have second layers and deeper structures, etc. So in fact, this linear neural network, it still describes some of a type of the linear transformation of our data X, by this whole matrix product, okay? F is just this matrix product times S. And as a consequence, it can reduce to the solution of linear regression if we take this matrix product equal to the solution of linear regression, okay? But we have more parameters, and it can be more flexible, for instance. And we also have this nonlinear version, okay? So we have this nonlinear neural network. And the main difference between linear and nonlinear neural network is that, so we still have some input at X and multiply by some weight matrices W1. And then we get this H1. And then we, at the level of each neuron, we apply entry-wise some nonlinear functions, okay? So this introduces some nonlinear transformations of the input data. And it describes a much complicated relation between the input data and the target, for instance. And then when we do the same thing, nonlinear transformation as the network go deeper. So this nonlinear so-called activation function, sigma, there are many popular used activation function. For example, the ReLU activation, the liquid ReLU, or the sigmoid sigma function. So in general, we have the model of nonlinear neural network given under the following form. So it's a linear transformation and entry-wise application of some nonlinear function, and etc., etc. Okay, so, but why we need deep neural networks, okay? Why we need so many layers? Well, because people in practice find that deep structures always gives us better performance. For example, in the case of handwritten digits classification, so on this popular MNIST data sets with just handwritten digits, and we want to understand to classify this image into the 10 possible classes of digits. Okay. And in fact, the linear regression solution give us a classification error rate approximately 12%. But if we introduce more layers, then the classification error rate decreases very quickly. And for example, with h equal to 4, so the number of hidden layer equal to 4 is already less than 1%. Okay, so in fact, deeper structure always bring good performance, but in some sense, it's more challenging to have to find good models because models are very, very huge. Okay, precisely. About 20 years ago, Le Gan introduced this LeNet, which is only 5 layer with approximately 60,000 parameters. And it's already pretty good to do very easy tasks, for example, of handwritten digits classification. But nowadays, about 5 years ago, I mean, things are much, much more complicated, and the network are just much, much deeper, because now we have, for example, more than 150 layers, and the number of parameters is really, really huge, okay? It's more than 60 millions of parameters. So in fact, to train such big models really require a lot of computational resources. And due to these huge models, we commonly use first order optimization methods to train these models. For example, gradient descent or stochastic gradient descent. But the problem is that this optimization, so due to the layer structure of the neural network itself, this optimization problem itself is non-convex, okay? Even in a very simple setting. For example, in the case of single hidden layer linear network, so h equal to 1, and the linear case, it's already a non-convex problem, okay? To say this, for example, we can minimize it's a single hidden layer between W1 and W2. Okay, so we have 2 matrices, and we would like to minimize the following difference, okay, between the target and the network output, for instance. Here we clearly say that, so if W1 star and W2 star is a good solution in the sense that this its associated loss value is very small, then this alpha W1 star and 1 over alpha W2 star is as good as the original solution. So in fact, there are many equivalent solutions in this neural network structure. And that is not a non-convex optimization problem, so it is very hard to train and to optimize in an efficient way with at least first order method. And due to this non-convexity, we see that there may be local minimum and very possibly also local maximum, and the most unfortunately saddle points, okay? All these possible constructions depends on the input and output and input data and its targets and the network design, okay? So because in fact, if we use first order methods of so in fact, the gradient descent itself can end up at any of this 3 types of points, because at this point the gradient equal to 0. Okay, so it can stop at any of the solutions. But clearly, these 2 later cases are not good because, for example, we hope to have a lower value of L, and in these 2 cases, we can always have, we can always have a lower value of L. Perhaps then we'll say, well, if you have a local minimum, that's good, but it's not very clear if it is the case, okay? For example, in this picture, we say that there are, in fact, 3 local minima, okay? But some of them are good and some of them are bad. For example, this is a bad local minimum in the sense that its corresponding loss value is very large. So this is a global minimum in the sense that it reaches the minimum value of the loss. This is, again, a local minimum. It's not global because it has strictly higher value of loss, but it is very closed. It has very good quality as well. And this loss value is close to that of the global minimum. So in fact, the non-convexity of deep neural network introduced many challenges. And in this picture, clearly we see that the performance of gradient descent is very sensitive to initializations. For example, if we start somewhere near this bad local minimum, and the gradient descent is going to end up in this bad local minimum, which we do not want. Okay, so the question we would like to ask here is that, can we still, so this is a challenging problem, and can we still say something on this difficult scenario, on this difficult problem? 12 remaining results. Okay, so we'll be working on this very elementary linear neural network model before we do more complicated nonlinear neural networks. And we will introduce some notations, okay? So input data and its targets, we'll like define some loss function. And here is a linear neural network model. We have a huge matrix product, okay? And that's what we're going to train all these weight matrices and possibly of different dimension, okay? And we're going to define this associated gradient descent dynamic given by this differential equation. Okay, so the state space is it's all the space of this different matrices of different size, and we define this gradient dynamic by this differential equation. So the time derivative of any w is just minus the gradient. Okay. So this defines a gradient system. And here is the conjecture we would like to prove. Okay, so it's global convergence to global minimum, which basically says that for almost every choice of input data and target, and almost every initialization of gradient descent algorithm in the state space, every trajectory of this gradient descent dynamic starting at W0 is going to converge to a global minimum of the loss. Okay. And that's a conjecture we would like to prove or perhaps disprove. So we'll first do some manipulation to simplify the problem, okay? We'll be working under the following classical assumptions that X, Y are both full rank. Otherwise, we can reduce to problems of smaller dimension. And we also impose that some condition on the dimension of the problem. Then up to singular value decomposition. In fact, we can, without changing the conclusion, we can reduce the problem to replace X by just an identity and Y by a diagonal matrix and some zero blocks. Okay, so we simplify these problems without changing its conclusion. And on this simplifies models, we'll introduce some notations. So this product of W is just a multiplication of different W's. And this M is in fact the error matrix between the target and the output of the neural network. Recall that we have X already simplifies to the identity. Okay, so now we're doing some calculus. We can show that the gradient dynamic is going to be given by this differential equation. And we're also defining the critical points, which are basically where the gradients, the gradient equal to 0, okay? So this equal to 0. And there, I mean, if you're at a critical points, then it's end of your gradient descent dynamic. You're not going to move anymore. So our first result is that every trajectory of the gradient descent dynamic is going to converge to an element of the critical points. So it's going to a point where the gradient is equal to 0. So the proof, okay, following the key remark that this dynamic is, so in fact, the loss function is, this is an analytic problem. So it's in fact a polynomial. So this dynamic is an analytic problem. So we can use Liao-Savage theorem, recorded as follow, which basically saying that every bounded trajectory of an analytic gradient system converge to a critical point. So we are playing with the analytic gradient system. So the only thing to do is to show the boundedness of all the trajectories. So in fact, as t goes large, all trajectory is not going to infinity, for example. And this can be done by introducing the following invariant structure of our gradient descent dynamic. So in fact, we can show that this difference of matrix is going to be conserved along this trajectory of gradient descent dynamic. And so that's, in fact, this difference is always going to be equal to some constant matrix that only depends on its initialization. And as a consequence of this invariant structure, we know that, in fact, all the Frobenius norm of our weight matrix is going to be equal to the weight matrix, the Frobenius norm of weight matrix of the last layer, plus some constant that only depends on initialization. So in fact, the gradient descent on training linear neural network, in fact, preserve many particular structures of the neural network. So there are many invariant structures in this dynamic gradient system. So since we have this relation, in fact, it remains to show that this Frobenius norm is always bounded, because at initialization, this is a fixed quantity. Okay. And we set GT equal to this, and we can, in fact, establish the following differential equations, which basically says that, so in fact, indeed, the Frobenius norm of the last layer is going to be bounded, even if t goes to infinity. And as a consequence, all the Frobenius norm of all the weight matrices is also going to be bounded. So that's good. We show that all this trajectory of this GDD is going to be bounded, and with Liao-Savage theorem, we proved it's going to convergence. And also, a very interesting consequence of this particular K invariant structure in neural network gradient descent dynamic is that, so with some particularly chosen initializations and network design, we can show directly an exponential convergence rate to global minimum. Okay, if in fact, if at initialization, so all this matrix, invariant matrix, satisfies some condition on its eigenvalue, then it's going to converge. So then the loss function and this gradient system is going to converge. So the loss function is going to converge exponentially to 0, and which corresponds to a global minimum. Okay, so to show this, we can establish the following a differential equation. So yeah, with a loss function here, and which is positive, positive or 0. So in fact, it remains to bound the following product of the minimum eigenvalue of all these matrices. In fact, we would like to find a lower bound that is strictly positive. Okay, and to do that, it remains to take, for example, consider the case where j equal to 1, and then this becomes the product of the minimum eigenvalue of all these matrices. that is closely connected to this WL transpose WL, okay? Because these two matrices shares the same non-zero eigenvalues. And in particular, this matrix is of larger dimension in our setting, okay? So then it remains to bound, in fact, the minimum, for example, the minimum non-zero eigenvalue of this matrix, which can be done via the control of our initialization. Since this second matrix is strictly is positive semi-definite. So that's it. And with a particular, so at least we established that with a particular choice of initialization, we can converge to global minimum, and the convergence rate is exponentially fast. And now we're going to consider the general case. What can we say in the general case of initialization? And of course, the dimension condition. We're going to introduce the following definition. So it's again, just product of matrices. So R is from W2 to WH plus 1, and the rank of it, and Z is from W2 to WH, okay? And we're going to decompose, in fact, the set of critical points according to the rank of our R matrix, okay? And then we'll denote, so the set of this is the set of the critical values of the loss function. So in fact, the value of loss function for W that belongs to one of the critical points. Then we have the following results, which describe the landscape of deep linear neural networks, okay? So assume that the target has distinct singular values, then we know a precise description of the set of critical values of the loss function. It's going to be the half sum of the square singular values of our target. And we know that the case of maximum rank critical points is a set of local and also global minimum, with the loss function equal to 0. So in fact, if the rank is maximum for this R matrix, then we're at the lowest value of the loss function, which is equal to 0. So in fact, in this problem, all the local minimum can be shown to be global ones. So that's good, but we still have, and we can also show, so it's not listed here, but it can also be shown that there is no local maxima. So in fact, it remains to deal with all this possible saddle points. And in fact, we know also some information about the saddle points. So we know that the maximum rank case is local and global minimum. And if the matrix itself is rank deficient, so we somehow lose rank, then it corresponds to saddle points. And in particular, if this rank condition is satisfied, then we know that the Hessian of this particular critical points has at least one negative eigenvalue. And we would like to mention that this first and second is already found in previous literature. But this third term plays an important role in our analysis. That we'll be talking about that in the next slide. Okay, so we know we have this proposition to describe the landscape of the linear neural networks, about the behavior of local and global minima, and also the saddle points. So now we would like to establish convergence. So for instance, for the moment with h equal to 1, so single hidden layer case with W1 and W2, okay? Then we can reformulate our conjecture global convergence to global minimum as follows. So for almost every pair of X, data X and target Y, we just need to prove that the union of basins of attraction of all saddle points is of measure 0. Since there's no local maximum and all global minimum are all local and all local minimum are global, it remains to in fact deal with all the saddle points. Okay, and we prove that this is true for the case of single hidden layer case, single hidden layer linear neural network with h equal to 1. Okay, which the proof rely on the concepts of normal hyperbolicity. Okay, so there is a little subtlety here because, in fact, we have some description of the Hessian of the saddle points. We know that if some condition is satisfied, then there is going to be at least so for a given saddle points, they're going to have at least one negative eigenvalue for the Hessian. So there is at least one direction to escape from this given saddle points. But the difficulty comes from the fact that there are a lot of saddle points in the state space. And if we just take the union of all the basins of attractions, so we just remove one eigenvalue for each saddle points, one eigenvector, one direction for each saddle points, and take the union of all this. And then depending on the geometry property of all these saddle points, it may occupy the whole state space, okay? So we need to know more, and that comes from, in fact, this concept of normal hyperbolicity. So intuitively speaking, it tells us that, so okay, we have this, let us formalize this intuition with this 3D illustration, okay? So consider this particular, so this given saddle points. We know that in the neighborhood, there are also other saddle points, okay? So in fact, this is going to describe by this red line, and all this x1 and x2 are also saddle points. Okay, so then if we do local linearization of this given saddle points x star, then we have its stable direction. So in the sense that it corresponds, for example, to the positive Hessian eigenvalue, okay? So then, in fact, the trajectory that coming from this direction will converge to this given saddle points. That's something we do not desire. In fact, we like those unstable directions, this WU direction, which comes from, indeed, the negative eigenvalue of the Hessian. So in fact, if the trajectory is in this direction, then we can, it's unstable and I diverge, and it does this escape from this given saddle points, okay? So in this three-dimensional example, we already know that there is going to be at least one direction that help us to escape from the saddle points. So, okay, but we are not sure how many directions that will converge to the saddle points. But the normal hyperbolicity tells us that the very important thing is that, well, if you move in the direction of the zero eigenvalues, so in fact, the zero eigenvalues correspond exactly to other saddle points where the gradient does not move. So what does that mean? It means that, so first of all, the union of basin of attraction does not contain this unstable direction, which diverge and escape from this point. And it also should exclude this direction. So this direction of zero eigenvalues, because in fact, this is the eigenvalue of other that corresponds to other saddle points. And if you move, and so if you consider this direction, the gradient is just not going to move. So in fact, for example, if you start at x1, you are not going to converge to this x star because x1 is also a saddle points. So its gradient equal to 0, and it's just not going to move. So in fact, when we count the dimension of the basins of attraction of this given set of points x star, we can exclude this unstable direction, and we can in fact also exclude this unstable direction, and we can also exclude this in fact central direction. So that helps to reduce the dimension of the basin of attractions for every given set of points. And then we consider the union of all these set of points. And based on this idea of normal hyperbolicity, that's enough to prove a global convergence. So that's enough to prove that the union of basins of attraction of all set of points is of measure 0 in the state space, and thus we have our conclusion of global convergence to global minimum. For the case of single hidden layer linear neural network with h equal to 1. However, this is no longer true as long as we have h, for example, bigger than 1. H equal to 2, for example. Then the direction that corresponds to 0 eigenvalue of the Hessian is strictly bigger than this line of other set of points. So in fact, in the case of 0 eigenvalue of the Hessian, we do not know much to say. So it's more involved. So it's more involved. Okay, here comes to our conclusion. So the takeaway message, there are very particular invariant structure in the gradient descent dynamics of linear neural network. So in particular, in the linear case, we specify its invariance of the matrices difference, but there are similar invariant structure in nonlinear neural networks as well, but is somehow, less. But those invariant structure are somehow weaker. Then the problem, as long as we have convergence of the trajectories, the problem reduced to somehow a global analysis of the union of basins of attractions of all set of points. So we should not guarantee, so the guarantee of a single given set of points is not enough, and indeed we need to consider the union for all set of points. And this is a continued times analysis, and therefore build upon the invariant structure. We do not need additional assumption on the norm of the gradients or the Hessians, etc. And here is a reference of this work. And thank you very much for your time and your attention.